Well, welcome to MV Tutors. I'm your tutor, Figa Manana, and today we're just going to do physical science. Okay, the topic we're doing is vertical projectile motion in 1D, and we're going to be doing a scenario 3 example or question rather. Now, scenario 3 is when you have a bouncing ball. Okay, but let's just go into the question real quick and read it up. So it says a ball is thrown vertically downwards from the top of a building and bounces a few times as it hits the ground. The velocity time graph below, so this is a velocity time graph, right? Describes the motion of the ball from the time it is thrown up to a certain time t. So time t is that final time there. Take downwards as a positive direction. Now they tell us this time what positive direction we should take. But normally you can assume it if you're not told. In this case we've been told, so we need to stick to that. And ground as zero reference. The graph is not drawn to scale. The effects of air friction are ignored. Okay, we're cool with that question. But before we answer the question, I just want us to demonstrate through a drawing how this would, what this bounce looks like. Let's choose a pencil over there. Okay, we'll choose it in black. Okay, let's make sure it's gonna give us a straight line. So let's say we have our building right here. That's our building. Okay, and then we have someone there. It doesn't matter who it is, but this person kicks a ball. Okay, so that's a ball. Right, now the ball is going to move from, this is the top of the building, and let's just do a bottom there. That's the bottom right there, like that. Okay, that's the bottom of the building. Now the ball, what I want to do now is just let me just do some draw the references that we will need. So we will need this reference here, that straight line there, and then that one too. So we'll have this situation. The next one is this one, or critical points, I'll call it that, critical points. The next one is that one there, and then the next one is that one there, just like that, and then the last one is this one here. Okay, so those are critical points. Now, okay, so the ball is going to drop from that building. It goes down, it hits the bottom there. At this point here, it's touching the ground, and then it comes back up. Okay, it goes a bit lower than the original position because it loses kinetic energy. It turns up there at this critical point. It comes back down to there. Okay, and it bounces. It's bouncing there. Okay, and then what happens from there is that that's the bouncing part there. It's at the floor, and then it goes back up. Okay, so that's the actual ball how behavior. Okay, so now that we've gotten this away, let's go and read the question. So the question says, write down the speed with which the ball is thrown downwards. Okay, so I like to use red to write my notes, my answers rather. So 3.1, write down the speed at which the ball is thrown. So they want the speed here, which it's thrown to the floor. And we can see that it starts at 10. So when they're throwing this ball, it starts at 10. It's at 10 meters per second. That's it. Meters per second. That's how you write it. Okay. And then 3.2, all parts of the graph have the same gradient. Okay, give a reason for this. Okay, so the reason they have the same gradient is because the gradient, first of all, let's start here. A gradient is, really a triangle like that. It's rise of, the change in the vertical over the change in the horizontal. So when we do that, we get acceleration. Okay, because remember, if you say meters per second, if you say meters per second, and then you divide that by seconds, which is what we are given here, the time is given in seconds, you get meters per second squared. Now this is acceleration. Okay, so in conclusion, the gradient represents the acceleration. Okay, so acceleration is the same, and if you remember, acceleration for a free falling object, it's 9.8. Okay, meters per second squared. Okay, I'm just gonna stop there. Let's go to the next question. All right, so the next question says, calculate the height from which the ball is thrown. Okay, so they want to know what is this height here. This height. That's the height we are looking for. Okay, so we need to get a formula. In choosing formulas, there's many formulas you could choose from. You just choose the one that you think is easiest, the one that has all the variables given. So I'm just gonna go ahead and choose one formula. I'm gonna choose the final velocity one, where final velocity squared is equals to initial velocity squared, okay, plus 2a, and then the change in displacement. Okay, so if we look very closely here at our variables, we can see that actually this distance is given by the velocity from 10, because it's thrown at 10, to the bottom. The bottom it reaches is 29.6. So the final velocity is 29.6. Okay, so we're gonna put 29.6 over there. Squared is equals to, the initial one is 10. Okay, remember we said anyway, it doesn't matter, anything squared is positive anyway. Now remember we said downwards is positive. Okay, so that means that we're gonna say plus 2, our acceleration, because acceleration of a free body, a free falling object is always accelerating down, so it's always positive if we've chosen down as positive. So, and then the change in x, that's the displacement we are actually looking for. Okay, so you put this in a calculator. All right, so let's just make this the subject of the formula. What we're gonna do is that we're gonna take the 29.6 squared, we'll subtract this 10 squared, because whenever you take anything to the other side of the equal sign, it changes sign. Okay, and then we'll divide by 2, that 2, and then and as well as that 9.8. Okay, and then that's gonna give us our change in x, which is the distance we're looking for. Okay, let me bring my calculator over here, which is put everything exactly as it is. So we have 29.6 squared minus 10 squared, and then at the bottom we have 2 times 9.8, and that gives us 39.6. Okay, so we have 39.6. Thank you. We'll just put that aside. So that, therefore, our distance, which is what we're looking for, is 39.6. Okay, so that answers the question. That's the height of the ball it was thrown in. Okay, and the units are meters. It's a very high building, 39.6 meters. Okay, so what's the next question? Next question is the time t shown on the graph. Okay, where's t? There's t. So we need to find this time here. Okay, so we need to find this time. Now you need to choose the right formula once again. So there are many formulas you could choose to do this one once again. You just choose the one that you prefer, the one that has all the variables that you will need to do the calculation. So I'm gonna go ahead and choose one that I prefer. I prefer the final velocity one once again, but not the one that is squared this time. I'm just gonna choose the normal one, which is Vf is equals to Vi plus acceleration once again and change in time. Okay, see the difference? If you're looking for change in time, these are not squared. Change in distance, these are squared, just like you can see. Anyway, let's go ahead and plug in the variables that you will need. So if we look at the final velocity from this graph here, you can see that the final velocity is 0, but the initial one is 8. So what we're going to do, sorry, let me check this out. The initial one is 25 minus 25, not 8. 8 is the number of seconds. So final is 0. The velocity of the initial one, velocity is a vector, so it comes with direction. It's magnitude and direction. That's a vector. So in this case, it's minus 25. Okay, now how do we know that? Because it's already been given in minus 25, and we know that from here to here, from there to there, this ball is going upwards, which is a negative direction. Remember, we were given downwards as a positive direction. So downwards is a positive, so our acceleration is positive. Okay, and then the change in time that we are looking for. Okay, so I'm just going to put this in a calculator. I'll take this to the other side. I have a positive 25 divided by 9.8. Okay, let's put this quickly in our calculator. Let's see what we get. So this time we have 25 divided by 9.8, and we have 2.55. One decimal, I'll just make it 2.6 seconds. Okay, now what you need to understand is that 2.6 seconds is from here to there. But we are interested in the entire, time. So we need to add this one from here, from the beginning to this. So it's going to be 8 plus 2.6 to get our final t. So t is equals to 8 plus 2.6, which gives us 10.6 seconds. Okay, that's our final answer. Okay, so over there we have that's 8 seconds, that's 10.6. That's it. All right, now what's our next question? Write down the time that the ball is in contact with the ground at the first bounce. Okay, so which one's our first bounce? This is our first bounce. So to that time that we're interested in is 2.2 minus 2. That was 3.4.1. 3.4.1. So it's 2.2 minus 2. What is that? 0.2, not 0.2 seconds. Okay, that's our final answer. 3.4.2. all right, says time at which the ball reaches its maximum height after the first bounce. So after the first bounce, this is the first bounce, so they want to know the time it reaches its maximum height. So it reaches its maximum height over there, and the time over there is 4.955 seconds. Okay, so we can just write that. It was 4.955 seconds. Okay, so it helped us to actually draw the actual bounce of the ball, because now you can tell that where it crosses there, that's where that's the highest point. Okay, if you hadn't drawn this, it would be easy to make mistakes, to assume the maximum height is either there or there, but this is where it is. Okay, so what's the next question? The value of x. Okay, where's x? X is over there. So what's happening at x? Actually, what's happening at x is that's where it leaves. Now this requires you to know a bit of theory. You can see that actually the velocity here, it's a theoretical thing, that the initial velocity is equal to the final velocity here. Okay, so if we look at velocity at this point, that velocity must be equal to the velocity at this point, theoretically speaking. And they told us that we can ignore all kinds of air resistance, so these velocities are the same. Now they're asking us the velocity there, so that means we must just look at the velocity, what the velocity is at this final point there. We can see that the velocity there is 27. Therefore, our velocity here in the beginning is also 27 because of that relationship. Okay, so that was 3.4.3. It is 27 meters per second. Okay, that's x. Okay, direction is minus, so we can give the direction as well, because velocity is always coming with a direction. So we can say 27 meters per second But since it's not required, you can put it if you want. If you don't want, it's okay. It's still, the answer is still gonna make sense. But let's go ahead and put it, because just for consistency's sake. Okay, now let's look at the next question. Is it the final question? Is the collision of the ball with the ground elastic or inelastic? Give a reason for your answer using the information in the graph. So this requires you to know a bit of theory. First of all, you need to know what does it mean for it to be inelastic and elastic. If something is elastic, then we are now talking about the kinetic energy involved. That's the initial kinetic energy has to be the same as the final kinetic energy. That's before and after contact. That's before and after the respective bounces. So theoretically, we know that it can not be elastic because the kinetic energies before and after the bounce are different. So we are going to choose inelastic. It's going to be inelastic because the speed before the bounce bounce is not the same after the bounce. Okay, so during the bounce, the ball actually loses kinetic energy to the ground. All right. Okay, we'll stop there. I hope you understood. Please, if there's anything you didn't understand, uh, feel free to contact us. You can just go to the comment section and comment, or visit our website mvtutors.co.za, and we will be glad to tutor you in this regard. Well, that's all from me right now. Enjoy the rest of your day. Goodbye.